So now let's try to learn what happens when metals react with water. So from our previous sessions, we know how metals will react with oxygen or air. So whatever is in the top of the reactivity series, they'll be reacting very, very vigorously. And whatever is at the bottom of the reactivity series, they will not react with air. And same thing goes hand in hand with water also. So to understand this, let us directly get into the format of how this happens. So when a metal, as you all can see on the screen, when a metal reacts with water, it forms a metal oxide and hydrogen gas. And again, if this metal oxide reacts with much more excess water, it forms metal hydroxide. So this is the format in which the reaction will take place if metal reacts with water. So when we make a metal react with water, first there is a metal oxide that is formed and also hydrogen gas is liberated. If the metal oxide is made to react with further water, you get a metal hydroxide. Now, as we can see, the metal oxide is getting used up. So the final product in this reaction, it is getting used up in the second equation. The final product will be metal hydroxide will be there and the hydrogen gas will also be there. And that those are the outputs that are shown in the following reactions. Now let us try to understand how each of the metal in the reactivity series will react with water. Okay, so let us start with the ones at the top of the reactivity series. We all know that potassium and sodium are at the top. So potassium and sodium will react violently with cold water. When we say cold water, it can also be water at normal temperature. The normal water, or when the water is cold also, it will react violently, which means there will be some kind of a splashing or an explosion happening in a minimal level. So the reaction is so violent, and also it is exothermic, which means a lot of heat is released. When we try to mix sodium in water or potassium in water, what happens is that it is so violent, it releases a large amount of heat because of its nature. I'm talking about normal water. And those reactions are given here. When potassium or sodium, if you look at the equations, react with water, they do form hydroxides. They form potassium hydroxide and sodium hydroxide. They release hydrogen, but they also release a large amount of heat energy, which is why the reaction is exothermic. So this holds good for the first two things in the reactivity series. So they will react very violently. When we go down the reactivity, this is the next one that we have in the reactivity series is calcium. So calcium also will react with water, but the reaction is less violent. It is not as violent as potassium and sodium, but it will be less violent. Again, heat will be released, but it is not too much. So what happens in the previous equation, the heat that is released will help the hydrogen to catch fire. So hydrogen, we all know it is a flammable gas, which means it can easily catch fire. So the reaction will catch fire. But in the second one, that is calcium, there will be heat energy that is released, but it is not sufficient for the hydrogen to catch fire. So it is less violent. And also the hydrogen that is formed, the gas that will stick to the surface of the calcium metal. They will stick to the metal surface, and that is why the metal will start to float. So this is very important. So when calcium reacts with water, a part of it forms calcium hydroxide, but there is still some calcium left unused in the reaction, which will start to float because the hydrogen gas that is released will start to stick to the surface of calcium and they will start to float. So this is also quite important. So as we keep going down in the reactivity series, the next one is magnesium. So magnesium does not react with cold water. It's quite obvious from the statement. Because it's down in the reactivity series, it's not that reactive, but it will react with hot water to form magnesium hydroxide and hydrogen. And this hydrogen will also stick to the surface of the metal and bring it to the top. Very similar to calcium. It will start to float because the hydrogen will stick to the surface. But the only difference is magnesium reacts only with hot water and not cold water. And as we keep going downwards, like aluminum, iron, and zinc in the reactivity series, they neither react with cold water or hot water, but they can react with steam, which is the next level of hotness of water, because after some time water becomes water vapor and it becomes steam. So now the metals like aluminum, iron, and zinc and all, they will react with steam. They cannot react with normal water, cold water, hot water, nothing. But they can react with water vapor or the steam. That is what is given in these two equations. If you look at the reactions, you can see aluminum and iron react with water, but interestingly, they are not forming hydroxides. they form only oxides, unlike the other reactions. Till now, we saw they form hydroxides. Because it is steam, it's forming only oxides. Because steam is in the gaseous form, it forms only oxides, and then we get hydrogen gas. So this is something that we need to remember. And if we go even below, like metals like lead, copper, silver, and gold, they will not react with any form of water at all. They will not react with hot water, cold water, steam, nothing. So that is something that we need to understand. Now, some of us will be sitting with the understanding of how will it react with steam? How do we produce steam and how do we react? For that, we need to understand an apparatus. So we do know how a metal will be put into cold water or how a metal will be reacting with hot water. But how does a metal react with steam is something that we need to understand. And this is a setup and apparatus given in the textbook. So what we do is, whichever the metal that you want to react with steam, that is taken here in the test tube. The test tube is placed horizontally and you take that metal sample. So probably, as we saw, the elements, the metals that will react with steam are, as you can see here, aluminium, iron, zinc. So they will be reacting with steam. So let's imagine it is zinc or aluminium or something. And then this is the metal sample that's being put here. And then there is a delivery tube, you can see, which is leading to a trough of water, and there is an inverted test tube kind of an arrangement, and bubbles are getting into. There is a stand which is holding on that and everything. But now there is something interesting here. They have used a glass wool soaked in water. Basically, glass wool is something that's used to, like run kites and all that. So it's like it's a woolen thread-like thing which is just soaked in water and it's kept. Just soaked in water and kept. Now, what happens when we supply heat using a Bunsen burner? This water will immediately vaporize and become steam. The water that is soaked in this will become steam, and that steam particles will react with this metal sample. So the hydrogen gas that is released during this reaction will pass through the delivery tube, and it will cause downward displacement of this water, which means as the hydrogen gas is getting passed through this tube, it goes upwards, because of which the water will be coming downwards. So slowly the gas will get filled in this inverted test tube, and we know that it is the hydrogen gas by testing it with the pop sound. When we take a burning candle near the mouth of a tube containing hydrogen gas, it will just create some pop sounds, squeaky pop sounds, and that is why we know it is hydrogen gas. So this is how we make a metal react with steam, and that's also test the output. That is, we test whether there is hydrogen gas by using some test. Now we are going to learn what happens when metals react with acids. We saw how they react with oxygen, how they react with water, now how they will react with acids. So the format for this is, when a metal reacts with a dilute acid, then it forms salt and hydrogen gas. So we are going to see some examples of this. So for example, let us take the case of, maybe we can take the case of aluminium. So aluminium reacts with hydrochloric acid to form AlCl3, aluminium chloride and hydrogen gas. So this can be one of the examples. They have not mentioned any chemical reaction, but this can be the case. So if a metal reacts with an acid, it forms a salt and it gives out hydrogen gas. It's mostly like a displacement reaction where this aluminium is displacing hydrogen and getting itself positioned over there. So this is how metals will react with acids. And as you can see here, hydrogen gas is released when metal reacts with an acid, but sometimes hydrogen gas may not be released depending on the acid that we are choosing. For example, if you choose hydrochloric acid, we will be getting hydrogen gas. If you choose sulfuric acid, we'll still be getting hydrogen gas. But what happens when we use nitric acid? So instead of getting hydrogen gas, we get water. And that is because this acid itself has some oxygen. Sulfuric acid also has, but this nitric acid is a very good oxidizing agent. What we call as oxidizing agent is they will be able to give away the oxygen easily. So that is why not always we get hydrogen gas when a metal reacts with dilute acid. Sometimes we may not get hydrogen gas also. And that's a very important question. So as you can see here, Hydrogen gas is not evolved when a metal reacts with nitric acid. Why? This is an important question from examination point of view. So what we just saw was nitric acid. When there is nitric acid, we get water. Okay, because nitric acid is a very strong oxidizing agent. What happens is it will be able to impart or give that oxygen, and hydrogen will become water. And it itself will get reduced to nitrogen oxides. So when you have nitric oxide, it will be able to give away the oxygen so that the hydrogen becomes water, and the rest of it will become any of the nitrogen oxides. Now, even within nitric acid, it will be able to give hydrogen only when it reacts with magnesium and manganese. All these are very important from 1 mark and 2 marks point of view.